So we have seen the definition of unification, and we have seen the definition of MGUs. And the question comes, if I give the two terms are given to me, how can I find a unifier? Or what if I want to find them MGUs? How can I do that? Okay. So to do that, first we need to understand when we know that we need to do something to fix the two terms so that they become equal some way. So there are places we need to identify the places where they're not equal. Okay. So they need a notion, the positions where there's a disagreement. Okay. So that definition is here. If I give you term T and Q, D1 and D2 are disagreement pairs. Okay. If D1 and D2 are subterms of T and U respectively, path to D1 in T, okay, is same as the path to D2 in U. Okay, so in the term T and term U, if you follow some path, exactly the same path, you reach to D1, and same path takes you to D2. Okay, and the root of D1 and D2 are different, so therefore they disagree. Let's see an example. Let's suppose we take these two terms. Okay, and if you draw this term as a path tree, then you obtain this kind of graph, and then we see, okay, where is the disagreement happening? Look at this node here. Okay, so this C, and at this point there's a Y. Everything is same. G is same, F is same, but at this point C and Y are not agreeing each other. So we can say that the C and Y makes a disagreement pair. Similarly, at this node, yeah, so H and D are disagreement pairs. Okay, so we can say that this two terms have two disagreement pairs, this and this, and this and this. Now, once we have a disagreement pairs, we want to make them equal somehow. Okay? So, but in some systematic way, let's see that algorithm. That algorithm is called Robinson's algorithm for computing MGUs. It not only gives you a unifier, it gives you a MGU. Yeah, that's very interesting. So initially you have a unifier which is basically doesn't do anything. Every variable renamed back to itself. So it's sort of very passive unifier. Okay, it doesn't really make T and U equal, but we start with some substitution, and eventually we'll get there and make it as a unifier. Okay, so while you are not unifying, for example, initially you may not be unifying, you keep doing it. Okay, so T sigma and U sigma is applied, and check that am I unifying or not. Then if not, then you carry on. Okay, find a disagreement pair D1 and D2 in this T sigma and U sigma. You pick them. If both of them are non-variables, okay, both of them constant, let's say C and D, you cannot really unify them. Yeah, and or one of them is f of x, another one is a g of x. Okay, so this is not possible, right? So both of them non-variable, then there is this unsolvable problem. You just say fail, you can unify. If one of them is variable, then the one which is variable, then you just call it x, and the one which is not a variable may also be a variable, you call it s. Okay, if x is the variable which occurs in S, you cannot make them equal, because if you substitute x by any other term, that term will be subterm of S. So you cannot really make them equal. So you declare them failed. Yeah. If none of these two failures happen, okay, then now you are ready to map x to S. And you say that now I'm going to update my substitution and update my sigma and move on to next iteration. As we move along, we have disagreement pairs. They will start reducing these disagreement pairs, and eventually I will run out of all x disagreement pairs, and I have my sigma is P MGU. Okay, let's suppose I want to unify this term and this term, okay, which was there in our example, and let's draw it out. Okay, and see there are several disagreement pairs. This pair, and this pair disagree with each other. So let's pick first one, this disagreement pair. Now what I'm going to do, x1 will going to map to this guy. Okay, so I will say that this is my disagreement pair, and I'm going to map x1 to gx2, and apply this map on my formulas. After this transformation, my formulas now at this stage. Okay, so now number of disagreement pairs should be decreasing now. Now the current situation is I have these two disagreement pairs. Now I'm going to pick one of them, let's say this guy, and we're going to apply this on the both the terms. Okay, so I obtain this new substitution and apply this on my terms, and I obtain this term pair. Now I have again still have some disagreements. Apply this in my substitution. If I do that, what happens is your sigma already has a reference to x2, and x2 is being updated here. So this update should also go in there. So when I apply it, then I will obtain this substitution. And if I apply this substitution on my terms, I will left with these two terms which are equal. So therefore I have unified them. Since no disagreement pairs are left, we are done. Our algorithm terminates. So remember that when you are trying to prove that this is produces contradiction, so then at that time we ask the question, is these two terms are unifiable? Now we have an algorithm, we run the algorithm, it gives us the these terms and then tells us, well, this is unifiable, therefore you can derive contradiction. The unification process is not a magic anymore. There's an algorithm which can do this for us.